Welcome to the Flip lecture series. This would be the first lecture made in this project. The goal is to not just flip the lecture, but it's also to personalize the lecture session for the students. Now, please do take note that it is crucial that you hold a writing pad and pen while watching this video, so you could write down any doubts or questions that you may have while watching it. And then I would need you to write this question onto Padlet via the link that I'll place in the description of this video. I will then use your feedback and questions that is on Padlet to design the activities that we will carry out during our actual lecture session this coming Thursday. Now, I will need your feedback and questions to be posted onto Padlet before end of Wednesday. Head on. So introduction, simple. If you could think about the products in daily life that is involved with chemicals, that's pretty much almost everything. So some of the common items would be shampoo, shower gel, hair gel, processed food. So some of the things that we use in a daily life. If you think about it, we start the day by brushing our teeth, and that uses toothpaste, which is a chemical that's produced by the chemical industry. Why are we talking about this? Simple, because this is essentially the core part of the lecture. We're going to think about how these chemicals that we use in our daily life is produced, and then what are the factors that goes into the thinking of a design. Keep in mind, we're not covering everything that's related to the chemical production, but merely we are thinking of the designing aspect of it only. Okay, so there's two types of manufacturing processes that is employed in the chemical industry. One is called the batch process. As the name would suggest, it is basically not. Just give me a second. Okay, I've selected my pen. Okay, hold on, pen. Okay, right, so it is not a continuous or mass production, meaning a batch process will produce the substances, so the products, in batches, which means they'll produce a batch and then they'll stop, and then there are some things that they will have to do, such as replenishing or servicing or cleaning up, and then they will continue the second batch. So each batch would then produce a very specific quantity of substances. That would be a batch process. And the other process that is quite the opposite would be the continuous process. This is a process that continues every day throughout the year, except for a very specific period where they will stop for servicing and maintenance. But essentially, it's a process that is continuous, and it receives the raw materials continuously to be processed and to be converted into products. So that's essentially two types of processes available. The decision of which process to be used would entirely depend on the kind of product that is being produced. Some example of batch processes: pharmaceuticals, drugs that is produced for medical industry, agrochemicals, which is substances like fertilizers, dye stuff, that includes hair dye or dye that's used in the clothing industry, food additives, perfumes, vitamins, pigments. Pigments are they are almost similar to dye, except pigments they tend to last much longer. For instance, pigments are the substances used in the car paint and so on. Continuous process, on the other hand, would be an example that you might be familiar: contact process, which is the process that produces a sulfuric acid, sodium hydroxide production, chemical that is constant, that's very commonly used in labs. Ammonia is one of the feedstock. Feedstock refers to the chemical that's used as starting a chemical reaction. So I'll just put here I want you to familiar with this term, feedstock. Feedstock is referring to a chemical that's used to start a chemical reaction, or it could be the primary raw material that's used to produce something. Ammonia is a very important feedstock for the production of fertilizers, which is, we looked at it as an example of a batch process. Ammonia itself is produced in a continuous process, and you're familiar with this. You learned this in your high school as the Haber process. Okay, so Haber process that produces ammonia in a continuous manner. As you can see that the the hydrogen and the nitrogen gas is continuously fed into the converter, which then converts it into ammonia. It's a continuous process. Petrol, as you would familiar with fractional distillation, which is a continuous process as well. Chlorine, methanol, these are some examples of continuous process. Now, some stages in the manufacture of a new product. So what are the general stages that involve, if you want to come up with a new product, how do you go about it? Of course, the very first step would involve research and development. Now, this is where you will have to look into what do you intend to produce, and what are the factors that you need to consider in producing this substance. And then, of course, you develop it. Once you pass that stage, you need to consider what are the laboratory processes that will be involved in this production of your substance. Keep in mind, we are talking about this in the context of a chemical product, producing a chemical substance. And then, of course, you start with the very first plant. Pilot plant refers to the very first plant. Generally, pilot plants are not too big because you're still trying out, you're still trying to see what are the challenges that you might come across with this production of this chemical. And then, of course, final production plant usually is something that you would be running at a full large scale. Now, the idea of, if you can see the flow of this is generally the scale of it tend to become bigger as you pass each stage. Generally, these are the stages in manufacturing a new product, chemical industry. Product. Okay, so now we're going to talk about in detail what are the factors required to produce a chemical product. Now, keep in mind, throughout this we are looking at factors, and I have tabled each factors to make it easy for you guys to analyze it. Essentially, each table is going to look like that. So we're going to have the factor at the side here, and then there's going to be the pros and the cons of each factor that we're going to look at. Okay, so some of the factors I may have grouped it to make it easier to explain, as they might be very similar to each other. Okay, now this slide essentially covers the feedstock. Now, I've explained to you what is a feedstock. Feedstock is the chemical that will be the raw material used in the production of whatever that you intend to make. For example, if you're producing ammonia, the feedstock for ammonia would be hydrogen gas and nitrogen gas. If the hydrogen gas is produced from methane through another process called steam reforming, then methane becomes a feedstock for it. Of course, if you're talking about contact process, sulfur dioxide will be the feedstock. Or if you're talking about fertilizer production, then ammonia becomes the feedstock. So feedstock is the chemical that we will feed into the process, the industrial process, to produce the product that you want. Now, the availability of feedstock is really, really crucial. If you design a reaction that uses a feedstock that is very rare, then automatically that is gonna cost you more. Or a feedstock that is simply not sustainable, which means it may not continuously be available. Then your investment into this industrial reaction may not last long, simply because the feedstock is not sustainable. So some of the pros and cons that we want to look at, I put it as pros and cons, but if you think about it in reality, pros means your industrial reaction will be profitable. Cons mean your industrial reaction is simply not profitable, or it's loss-making. Now, you have to think about it in terms of profitability or loss-making, simply because it may not be something that you can run if it's loss making. I mean, logically thinking, nobody would be running an industrial reaction that is loss making, not even the government. No matter how important it is, if it is loss making, then it becomes something that is simply not sustainable and it's not economically viable. So some points to think about. So you're designing an industrial reaction, you intend to do it, for instance, in the place wherever you are in your country. Then the local availability of the feedstock usually keeps the cost down. Now keep in mind, it keeps the cost down and it helps you maximize your profit. Now, profit is not a bad thing. Keep that in mind. Profit is good because it allows you to reinvest into your industry. It allows you to pay your workers well. It can be something that you can use to contribute back to the society. Of course, some of the cons that sometimes it's simply not possible for the feedstock to be available locally, and that if that's the case, then you do need to think about, okay, what are the transport costs if you have to sort of import it in, or you will have to transport it from a place to wherever you are. You do need to think about what are the safety and environmental consideration of transporting this feedstock and processing it in your place. Keep in mind, if your feedstock is rare, then you may think about what is the cost of buying it, because if it is too expensive, then your end product will become very expensive, and a very expensive end product may not be very attractive for people to buy, and as a result it could end up being something that you will be at loss in producing it, because simply you can't sell it. Energy derived from oil and gas fluctuates in pricing, meaning if you are designing a reaction that requires energy that comes from oil and gas, the sustainability of it is one issue. Second, pricing may fluctuate, so as a result it may affect your the process of your production. Okay, let's look at another factor. Excuse me. So the other factor that we're going to look at is the opportunity for recycling. So what is the what this simply means is you want to think about, is there an opportunity for you to recycle? Now, what do I mean by recycle? There's two things that we have to look at in a chemical reaction. One is, that it's almost impossible for us to achieve 100% efficiency, meaning not all of your reactants will be reacting completely to form products. There's usually some amount that is left behind, and common industrial efficiency is between 70 to 80%. Some reactions slightly more, but it's never 100%. So is there an opportunity for you to sort of take the unreacted materials and sort of feed it back? Can you design it in that way? For instance, if you think about it, Haber process has it's not 100% efficiency. Some hydrogen gas and nitrogen gas may not react. We need to think about how can we channel it back into the reactor, so this sort of ensures that we are not increasing wastage. Now, speaking about wastage, that's another thing to look at. You want to think about, is there a waste product being formed in this reaction? If there is, then you want to think about if the waste product can be used for other purposes. Can the waste product be manufactured into a different product, or can it be packaged and sold, or can it be used to increase the efficiency of the existing reaction? Now, I believe we will talk about this again in another part, but recycling is huge. It is something that almost all industrial reaction thinks about, and because it can be something that can support us financially. Recycling could be a source of income for companies. It can also be something that will be very environmentally important. Okay, some examples are, of course, pros. I spoke about unreacted materials already. Feeding it back into reactants, of course, increases efficiency. We want to think about water. If your industrial reaction does use water, can it be recycled? Can the water be reused rather than for you to be bringing in new water into the reaction? Is there a way to recycle? Of course, again, this is just suggestion. Not everything, all industrial reaction can be processed this way. Some cons is, of course, these are things that are going to stand in your way. When you think about recycling, it's sometimes very difficult to separate unreacted starting materials or the feedstock. So when it becomes very difficult to separate, the opportunity for recycling tend to decrease. When that happens, of course, wastage and cost. Why is there a wastage relationship to cost? Because very often you may have to spend in order to deal with the waste, because now there are laws that protects environment and the people, so you do have to be responsible enough to think about what can you do with the wastage. Okay, let's move on to another factor. Energy requirements. Now, this is probably one of the most important factors, because if you don't consider this at the start of your design, it can very severely affect the way that your reactions will run. Now, energy requirements refers to literally, does your reaction require energy? The answer is yes. Unless we are talking about a spontaneous reaction. Even in the case of spontaneous reaction, it may release heat. So you do have to deal with this heat. Or some reactions that requires heating. Again, I'm going to quote a reaction that is very familiar with you guys, the Haber process. You need to think about heating. You do need to heat the converter. So what kind of energy requirement that it will require, how much is the input, and how are you going to mitigate any issues that may come into that. So exothermic reaction, for instance, they are generally good. People like exothermic reaction because the reaction itself produces heat, and the heat can also then be sort of channeled back into the reaction, sort of to maintain an optimum temperature, or excess heat can be sort of nicely removed and used to sort of heat the building. In countries where they're generally very cold, you require to heat the building to keep it at a comfortable temperature. So heat can be channeled in that way. Of course, it is a suggestion. Whereas in countries that's very hot, obviously they will have to think about how do they cool the reaction. What kind of energy is required to be spent on cooling? And keep in mind, cooling is a very energy consuming process as well. Then of course automatically that becomes your con. Of course you're doing it in a country that's very hot, you need to sort of cool it, and that of course would need energy. Catalyst usage is very important. In fact, it's one of the components of green chemistry, which I will talk about towards the end. Usage of catalyst is very important. So at the design stage, you do have to think about, is that catalyst available for my industrial reaction? Because using catalyst generally lowers the temperature required. So that means you will be able to use less energy if your process requires heating. All right, and this directly sort of reduces the cost that you will be spending, because one of the major costs of running an industrial reaction is the energy requirement. Next factor, don't worry, that's not that many factors that we are looking at. Okay, use of byproducts. Now, byproducts, keep in mind, byproducts are not necessarily waste. Generally, we classify something as a waste if there is no further use for it. Byproducts, on the other hand, can have further use. So you do have to think about it if your reaction produces any byproduct. Some byproducts can be collected and sold separately. One example that I can think about is the electrolysis of brine, which is a process that is used to produce sodium. One of the byproducts is, of course, chlorine. It's a toxic gas, but chlorine itself has its own industrial uses. So if we can design it in a way that the chlorine is collected, which they do, and that can be used, that can be sold separately. Another example that I want to quote that you might be familiar with is the purification of aluminium. So if you know aluminium bauxites, that's the formula. So that's aluminium ore, essentially. When we mine it, of course, one of the major products in it is aluminium oxide with a lot of other things. But when we electrolyze this, essentially what we get is aluminium. That's what we want. And one of the byproducts that it produces is oxygen. Now, this oxygen can be collected purified and sold separately. Oxygen is a very important substance in the medical industry. So that's an additional revenue that can be generated. So this is just an example. You do have to think about, if you're designing a chemical reaction, is that going to be a byproduct? If there is a byproduct, can it be sold? Is there a market for it? If there is, then you need to think about how are you going to collect it separately. All right. And in the case where, well, the byproduct is it does not have any industrial use, then you do have to think about, is it toxic or corrosive, or is it something that is environmentally damaging? For example, carbon dioxide. Carbon dioxide is environmentally damaging. There are laws that protects the environment against a certain amount of carbon dioxide emission. So you do then have to think about how you're going to deal with this byproducts. And there has to be a proper way of dealing with it, and that would generally cost money. So you do have to think about it at the design stage. To speak about carbon dioxide again, it is a greenhouse gas, and sulfur dioxide is known as an acidic gas that causes acid rain. So you do have to think about how are you going to deal with it, and you do have to incorporate it into your design. And yield of product. Now, again, this is another factor that is linked to the green chemistry factors that I will talk about later. Yield of product. If you decide to produce something, and I want you to think about it, your product that you're going to produce, you do have to study it at the laboratory stage to see what is the percentage of yield that the reaction will give you. Now, it's something very important to think about, because, you know, if you have designed a reaction and then you realize at the end of it that it produces a very low yield no matter how you influence it, and it's going to cost you a lot to run it at each batch, and that low yield can really affect your profitability. Now, keep in mind, if it's not profitable, then it will not be wise to run it, because it will not be a sustainable industrial reaction. Okay, so this is a very important process. It's linked to the green chemistry as atom economy. You do need to think about what is the yield, how can we influence the yield, and how can we reduce wastage. Of course, reactions that is low in yield will consume more money, and of course, in order to increase the yield, you may have to run the reaction longer, and that would of course cost you more. All right, rather simple factor and very straightforward. Okay, so this is the last thing, last factor, safety. Now, safety is a very important factor. There are safety laws internationally and for each country specifically governing industrial reactions. You have to be aware of it. You have to have people who is specializing in it that will have to work with you in your industrial reactions. So you do have to comply in this. There's no two ways about it. So one important thing that we say, it's a process safety management, meaning once you've designed your industrial processes, you do have to think about managing the safety, as these industrial processes will have a continuous risk that it will pose to the environment and to the people who are working on it. Very important question to ask ourselves during the industrial design: what if something goes wrong, or what if this does not go the way you want it? I'll give you a simple example for your imagination's sake. You design an industrial reaction that requires heating at high pressure. Now, that's two of the most dangerous combinations. We're talking about very high pressure vessel, and it requires heating. I think one simple example would be a contact process, or even the Haber process, though the pressure in it is not that high. The idea is, when this is combined in the reaction vessel or in your converter, you need to think about what happens if something goes wrong. You need to think about what are the risks that it will pose, and how do you intend to manage this. Keep in mind, we're not going into in detail with safety. Obviously, we will not be doing how these risks are managed or mitigated, because that's obviously not done at the foundation level or at the pre-university level. It's generally a course on its own. But this is something that I need you to be aware. We need to think about safety factors when we design a chemical reaction. Now, a part of how we do it is called risk assessment. We assess the design and we think about what are the risks that might be involved. I've got a small exercise coming up next for you. Just give it a try. I want you to use your general logic to assess what are the possible risks that might be involved, and what are the simple things that we can do to sort of mitigate the risk that comes with your industrial design, industrial reaction. Okay, so this is one of the most important thing. It's key to review the design. At the design stage, keep in mind we are at the design stage. You need to sort of think about what are the what can you engineer to sort of mitigate this risk that is involved in your design. Some risk can be sort of engineered out of the process, which means you can completely remove it. Some you can't. When you can't eliminate it, then you need to seriously think about how can you reduce the risk, since you can't completely remove it. Okay, so take a good look at this. Is just an example of an industrial reaction. I picked fractional distillation because you might be familiar with this from your high school. Of course, it's not an actual industrial outline, but generally this is how it is. There is the crude oil supply that you can see. Oops, sorry. You can see that crude oil supply, this is your raw material that's coming into here. And then you, of course, have got a boiler. What is a boiler? It's a superheated steam that's used to increase the temperature. And then you can see that this is your fractional distillation tower, in which you have different compartments with a different temperature, which then sort of causes the condensation of a different distillate. Now, in the upcoming quiz, I want you to identify simple risk and probably what are the things that can be done. So that's based on this design. Take a good look at it. Probably you can grab a piece of paper and jot down what are the risks that you can see in this design, and what are the simple things that can be done to manage the risk that is involved in this industrial process. So take a good look at it, take a piece of paper, maybe you want to pause it at this point, and then write down what are the risks that you see, and the link will show up for the quiz, which you can give a try. Okay, moving on, just coming to the end of this video. I'm trying to keep it as short as possible. Key environmental considerations. So far we talked about the factors involved in the design. We talked about safety. Now we're going to talk about environment, because it's really important for us to design a reaction that has that meets the environmental requirement that is set out by international local laws. Some government requires you to meet the conditions for them to give you a license to operate, and of course your own responsibility as a human being to the environment. Now, again, it is something you have to consider at the design stage and not once your factory is up and running. You have to think about it at design stage. Again, the key, the same as the safety, key here is you want to eliminate or minimize anything that is possibly posing a risk to the environment itself. If you can't eliminate, then you do have to think about how can you contain it. For instance, if your reaction produces a carbon monoxide as a product, as a byproduct, as a waste, you need to think about how are you going to trap it, because it is extremely toxic. How are you going to treat it before you release it? And you need to think about what are the national laws and international laws that you will have to meet in order to operate within the safety environmental safety means. This involves you minimizing your waste as much as possible. Of course, avoiding toxic product as much as possible. Keep in mind, if you can't eliminate them, then you have to think about containment and treatment. Now, keep in mind, this point here comes at the stage where you think about you can't eliminate it, then you have to think about that. All right, and of course, this is ideal. We want to design a product that can biodegrade as much as we can. Right now, there is a push for that. The entire world is moving towards that. I believe we are looking at more and more ways of designing whether new products or existing products in a way that it will biodegrade very easily. And for those who don't know what biodegrade is, which means the substance, once it's being used, once it's thrown out to the environment, it will break down in a safe manner, not releasing any toxic substance that could harm any living organisms or the soil. That's the meaning of biodegrade. So again, this is crucial. There are no laws yet that dictates that the product must biodegrade, as much as I can remember. So, but it might be something that will be in the future. So it's something really worth looking into. Designing a product that can biodegrade could also boost its sales, since the awareness among people to buy things that no longer harm their environment has increased tremendously. Okay, moving on. We have come to the end. Now, there is 12 principle of green chemistry. In the next 2 slides, I'll just briefly explain to you why do we have principles of green chemistry. This is a principle that has been internationally recognized. Things that these are the framework that is used to design or improving materials. Now, how I want you to look at this green chemistry points is, I want you to look at it, and of course, you do have to remember the 12 points here. Try to link it to the factors that I've talked about earlier. For instance, you can see the first point here, which is the preventing waste. You know that we talked about this earlier in the factor when we said that we want to maximize yield, or we want to recycle, to look at the opportunity of recycling the unreacted substances. And that also relates to atom economy. Atom economy means, you know, maximizing yield so that you are using the exact amount of reactants that you need or close to that. Excess means it produces more waste. And I talked about this in terms of designing a product that that may not produce a toxic byproducts, or you know, even producing something that is not involving very dangerous chemicals. Design benign chemicals. This can, of course, this is a very big thing, a very big point, but we want to simplify it and think about it in this way. When you design your chemical, if once it is thrown out, will it biodegrade in a very environmentally safe way, or will it break down into a very toxic or harmful substance? So that's quite an important thing to look at. So what I want you to do is, I want you to look at each of these points. I want you to think about how can it link back to the factors that I've explained in detail in the early part of this video. So everything is relatable to it. We talked about catalysis, meaning catalysis here to use a catalyst that will lower the energy requirement. So that sort of links back to the point number 6 here, designing to increase the efficiency of the energy, renewable feedstock, reduce derivatives, which means, you know, trying to reduce the byproducts that may not be useful or that are harmful for the environment. This is again talking about the biodegradable part of the product. You want to think about pollution. This is, you know, sort of analyzing it to think about the environment, and of course inherently benign chemistry for accident prevention. This is a very important thing. This relates to the safety of the entire industrial process, to think about what can we do if there is an accident, what can we do to prevent it from harming people or the environment. Okay, so you do not have to be able to explain all of the green chemistry in detail for your exam, but you do have to know how do they link to the factors that I have explained earlier. Okay, now some points about green chemistry. So they are simply based on a set of principles that's used in the design, development and implementation of chemical products. It helps us as scientists to protect and benefit the economy, people and the planet, so inclusive of all. It uses renewable biodegradable materials which do not sort of persist in the environment continuously, like plastic. Obviously green chemistry is against plastic that are not biodegradable. Of course, you try to use catalysis or biocatalysis, or, you know, together. Biocatalysis refers to usage of microorganisms, for instance, that improves the efficiency and helps us conduct reactions at much lower temperature, because, you know, the more heat you produce, the more fossil fuel consumption takes place, and that's not really good for the environment. Green chemistry is a proven system approach, which means this is proven to be possible. It's been done, therefore it is endorsed internationally. It reduces the use and generation of hazardous substance, and of course, it offers a strategic pathway to build a sustainable future. Okay, so we have come to the end of the lecture. So now what I want you to do is, there's going to be a link at the end of this, and there'll be a link at the description. I want you to click at the link, and it will take you to Padlet. I want you to post your questions on this lecture. Now, if you have not been writing down your questions throughout the video, please just revisit the video. You want to forward and probably look at some parts that you may have not understood very well, or you think you want to hear more explanation from me on some parts. I just need you to indicate it in the Padlet. The Padlet, you can make write your comment on the Padlet till end of Tuesday, approximately 12 midnight, because Wednesday morning I will look at the Padlet, and then I will develop the materials required for our discussion, my further explanation to you on Thursday morning lecture. Now keep in mind, this is the very point where I'm personalizing the lecture for you guys, thus the idea of a flipped and a personalized lecture. Please write down your questions. Padlet allows you to post your questions anonymously. When you are on it, please take a look at what are the questions posted by your friends, so you don't have to repeat some of the questions. But if you do want to repeat, and you have a different focus on it, go ahead, just write down whatever that you want me to re-explain or explain further, or you think something that you are curious about or you're interested about hearing more. Please do write it there, and on Thursday, as I've promised, the first hour will be utilized to answer your questions, and the second hour we will use it for hands-on activity that will enhance your understanding for this lecture, and most of it will be games. Okay, thank you very much for listening, watching this video. I really hope you would cooperate by giving your questions at the Padlet, and please do encourage some of your friends that have not watched this. Please do encourage them to do so. Thank you very much.